In this video, we will discuss the solution to problem D, array collapse, from educational round 160. You are given an array containing n distinct elements. In one operation, you can select any subarray and replace it with its minimum value. So for example, you can select this subarray 4, 7, 5, 2 and replace it with the minimum value of 2. Now you are asked to find out the number of unique arrays that you can achieve by applying this operation any number of times. This is a short summary of the problem. To help you understand the concepts discussed in this video, I have created some standard problems and added it to a Codeforces contest so that you can submit your solution and verify whether it is correct or not. So if you go to cfstep.com, this is the URL, and if you click on that Codeforces logo over here, you will be redirected to the Codeforces group. In this Codeforces group, I have added a contest called Monotonic Stack plus DP, and I have created these two problems for now so that you can submit your monotonic stack template and verify whether it is correct or not. And this problem is basically for verifying whether your brute force, that is O of n square solution, whether it is logically correct or not. And this is the original problem on which the video is targeted. Right now I haven't added the pretty basic ones such as the next greater element, previous smaller elements, etc. But if you do want me to add them, please let me know in the comments or on Codeforces, and I will create the problem and add it over here. Let us try to solve an easy version of this problem. Suppose that you have an array containing these 5 elements. Now in the final array, you do not know what the last element of the final array would be, but you can say for certain that the last element has to be one out of these 5 elements. Either it could be the white element or the blue element or the pink element and so on. So this prompts us towards a DP definition wherein we define DP of I is the number of reachable arrays that are ending at I when we only have the first I elements. So DP of 3 would represent the number of reachable arrays of this segment that necessarily end at I. Using this DP definition, later we will see how this can help us in answering the original problem. Next, we'll see a very easy and intuitive algorithm to populate this DP array. Let us start with one element. If you have just one element, then there is just one way for the array to end at this element. Hence, DP of 1 would be 1. Now, what happens when you introduce or append a green box at the end of the sequence? What would the DP value of this green box be? Of course, the DP should ensure that the green box is the last element of the resulting array. So we append it over here. But what about the second last element? It could either be the pink box or it could be empty. Hence, if we could find out all possible configuration to achieve the second last element, then we can go to that configuration and append a green box to achieve a configuration that ends with a green box, right? But there is just one small challenge, that you cannot append a green box blindly anywhere. So for example, if you have the array as 1, 2, then you cannot achieve this configuration, right? Because 2 can never clear out 1. But with an array of 3, 2, you can achieve both of these configuration. So how do we figure out when is it okay to append a green box and when is it not? Let us append a blue element at the end. To compute the number of subarrays ending at the blue box, we need to make sure that the last element is the blue box. But what about the second last element? It could either be the green box, the pink box, or it could be empty. Now let us see when this configuration is possible. You can see that the green box from here has vanished. When can a green box vanish? It can either be eaten by the pink box or it can be eaten by the blue box. When can it be eaten by the pink box? Of course, when the pink box has a value that is smaller than the green box. So for example, in the case of 1, 2, 3, 1 can eat 2. And when can it get eaten by a blue box? If the value in the blue box is smaller than this particular value. So for example, in 5, 4, 3, you can see that 3 can eat 4. Let us append an orange box at the end. To compute the number of subarrays ending at the orange box, notice that the last second box could either be the blue box, the green box, the pink box, or it could be empty. Let us talk about when can this configuration be valid. That is, when can a pink box and an orange box be adjacent to each other. You can notice that all the elements in this segment have vanished. When can they vanish? They can only be eaten by this box or this box. Hence, if you notice that if you compute the minimum element on this segment, including both the endpoints, the minimum element has to be this one or this one. Because if the minimum element of this entire segment is this here, then nobody can eat it, right? And this configuration can never be achieved. So for example, if you have the pink box as 3 and the orange box as 1, you can see that 4 can be eaten by either of these, but 2 can only be eaten by 1. So in technical terms, you can say that a range is only valid if either of the terminal element, including the endpoints, is the minimal element of the range. Let's append a white element at the end and figure out how to compute dp of white based on all of the previous colors. Of course, the last element would be white and the second last element can be either of these. So let's focus on this configuration. Of course, it is very easy to figure out whether this configuration is valid by checking if this subarray has a terminal minima or not. So now suppose that this configuration is indeed valid. Then you can see that in all of the configuration of two elements, such that the green element is the last element, we can append this white element at the end to get a configuration in which white element is the last element. Hence, dp of green would contribute to dp of white. And if you follow this similar reasoning, you can see that dp of white is sum of dp of color such that the dotted lines represents a subarray with a terminal minima. So far, we have computed the number of subarrays ending at a particular color. But what if this was the original array of length 5? What would the number of reachable arrays be? Is it just sum of all the dp values for each color? That is not correct, because if this is the original configuration, then you can see that in the final array cannot end at 3 nor can it end at 2, because these two elements cannot clear out 1. So if you think about it, in the final array, a dp will only contribute to the final answer if this element can clear out all the elements to the right of it, right? Only then it can end at this element. So the answer would be sum of all dp color such that the minima of this range is equal to this. The implementation is pretty straightforward. You keep on adding elements one by one, and for any element at the ith position, you make some choices on the second last element. Of course, it can only be towards the left of the ith element, so you iterate over all of them, and then you see whether that is a feasible second last element or not. Of course, it will only be a feasible second last element if this subarray has a terminal minima. That is, all the elements in the inner range should be able to get eaten by the left terminal minima or the right terminal minima. If it does, then you increment the DP contribution. And the second case is that there is no second last element, and that is only possible if x is the minimum element on this prefix. So if that is the case, then you increment this DP count by 1. And at the end, make sure to only count the contribution of DP for those elements which are suffix minima. So this is a pretty simple code that solves this problem, but the time complexity is O of n square because we run two nested for loops. So in the later part of the video, we will see how to optimize it from O of n square to just O of n. Let us formally define a right terminal minima. R is said to be a right terminal minima for L if the minimum element of this subarray lies on the rightmost element of the subarray. For example, if you have a subarray starting from the green element and ending on the orange element, and also suppose that the orange element is the minimum element of that subarray, then you can say that orange element is the right terminal minima for the green element. Vice versa, if the green element is the minimum element of that subarray, we say that the green element acts as the left terminal minima for the orange element. So given any particular index, how do you efficiently find out the number of times it will act as the right terminal minima? If you have this white box, you can compare it with the orange element. So if the orange box is greater than the white box, it means that the white box will be the right terminal minima for this range. Then consider the blue box. If the blue box is also greater than the white element, then the minima would be here. So it will again act as the right terminal minima. And you also see the white arrow on this green box. So it means that green element is the first element to the left of the white element that is smaller than white element. So since it is smaller, it cannot, so the white element cannot be a minima anymore, right? So it is very easy to see that white will keep on acting as the right terminal minima until we encounter the previous smaller element, and from that point onwards white can no longer act as the right terminal minima. And finding out the previous smaller element is a pretty standard task that can be done via monotonic stacks. But how do you find out the number of indices to the left of the white element that will act as its left terminal minima? So this requires a clever observation which we will see in a while. In this diagram, orange is the previous smaller element of white, blue is the previous smaller element of orange, green is the previous smaller element of blue, and so on. And the dotted lines are the elements that are in between the PSEs. So a data structure that can store all of these solid bars together is stack. So you push all of these on the stack, and when you are adding a new solid bar, you traverse the stack and pop all the dotted lines. Basically all the elements that are bigger, you pop them out till you hit the next PSE. So then the stack will contain only the solid bars. Now focus on this particular area. So in this particular area, all the elements are of course greater than white because this is the first PSE. So for this range, white will act as the right terminal minima, which we have already figured out. But what will be the first left terminal minima for white? So notice that orange will be the first left terminal minima because the minimum of this range is of course orange. Now can you figure out the next left terminal minima? In fact, it is the blue bar. It cannot be anything in between because if you take the minimum of this range, it will land on the orange bar. So blue bar is the next left terminal minima. What is the next left terminal minima? It is in fact the green bar because if you take this minima, it will land on the blue bar. So in fact, if you have white, then the number of indices that can act as the left terminal minima is the count of solid bars on the left. So if you want to count all of their DP contribution, you can just keep a variable that keeps the sum of all the DP values for the elements that are on the stack. So using this technique, you can get the contribution of the left terminal minima in O of 1. And we also previously saw that using prefix sum, you can get the contribution of the right terminal minima in O of 1 using prefix sums. So this is a very powerful observation that the when you do the stack method to find out the previous smaller element, at any point in time all the elements on the stack, they represent the left terminal minima for this particular index, and all the element in between, they will contribute to their right terminal minima. So this technique can help you solve a lot of problems that involves minimas and maximas on subarrays and monotonic stacks. So now we will look at the implementation of this particular idea. The code is pretty simple. We will just simulate the strategy with the solid bars and dotted bars that we saw on this particular slide. So we process the elements one by one and we assume the current element to be a solid bar. So if it is a solid bar, it will pop all the dotted bars. Dotted bars are the ones with a greater value. So it will remove them from the stack. And once that is done, the topmost element of the stack is guaranteed to be the PSE, right? It is guaranteed to be the PSE. So it means that we need to add the prefix sum for this particular range. It means that we need to add the DP sum for this particular range. So we can get that from this query function. So this query function is nothing but prefix of R minus prefix of L minus 1. So this is the query function. So this is the contribution of the right terminal minima. What about the left terminal minima? We already discussed that all the left terminal minimas are the ones that are already on the stack. So we maintain a variable called DP values sum on stack, and when we pop it from the stack, we remove the contribution, and when we push it on the stack, we add the contribution. So at any given point in time, it will contain the sum of all the DP values of the left terminal minima that are on the stack. So these are the two independent contribution that we discussed in this particular slide. So this is the prefix sum, this is the DP values on the stack, and you can see that since we are iterating over all the elements at max once or twice, the time complexity is O of n.